LU Decomposition. In this lesson we discuss LU Decomposition, which is a variation on Gaussian elimination for square matrices. Unlike Gaussian elimination, LU decomposition is performed on the original matrix and not the augmented matrix. Recall the three elementary row operations. Each of these operations can be performed by applying an elementary matrix. To interchange two rows, we apply a permutation matrix. For example, this matrix interchanges rows 1 and 2 of a 4x4 matrix. This matrix interchanges rows 2 and 4 of a 4x4 matrix. We can apply a matrix to multiply a row by non-zero scalar. This matrix multiplies the second row by 5. We can also apply a matrix to add a scalar multiple of a row to another row. For example, this matrix adds 3 times row 1 to row 2. This matrix adds 2 times row 1 to row 4. This matrix adds 2 times row 4 to row 1. And this matrix subtracts 6 times row 2 from row 4. In this lesson, we will use only the third operator. This way we do not change the values of the pivots. This will give us a simple and unique separation of a matrix called its LU decomposition. Consider this 3x3 matrix. Let's reduce this matrix to row echelon form, by only adding scalar multiples of rows to other row. We start in the first column. To zero out the element below the first pivot, we need to subtract 2 times the first row from the second row. This is the same as applying an elementary matrix, which adds -2 times the first row to the second. Okay, here's the resultant intermediate matrix. Now, we need to zero out the bottom element in first column. We apply an elementary matrix, which adds -3 times the first row to the third row, and this is the resultant intermediate matrix. We now move to the second pivot. To zero out the bottom element, we apply an elementary operator which adds the second row to the third row. The matrix is now in row echelon form, which for square matrices, is an upper triangular matrix. All the elements below the diagonal of an upper triangular matrix are 0. We'll call it U. Then E3, E2, E1A equals U. Let's look at what this says about the original matrix A. We can move the operator E3, E2, E1 to the right-hand side as an inverse. We already know explicitly the value of U, so let's find the value of the inverse of the product of elementary matrices. To take the inverse of a product, we need to take the product of the inverses in reverse order. Here are the elementary matrices we just used for row reduction. Rather than compute the inverses of each matrix explicitly using Gaussian elimination, which isn't hard but tedious to set up, we can just think about of each inverse as an undoing. If we subtract 2 times row 1 from row 2, in the inverse, we add 2 times row 1 to row 2. If we subtract 3 times row 1 from row 3, in the inverse, we add 3 times row 1 to row 3. If we add row 2 to row 3, in the inverse, we subtract row 2 from row 3. We still need to multiply these three matrices. Every element above and to the right of the diagonal is 0. Such a matrix is called a lower triangular matrix. Furthermore, the diagonal is all ones. We call this type of matrix a unit lower triangular matrix. It should not be surprising that the product of unit lower triangular matrices is itself a unit lower triangular matrix. What is a little surprising is that the subdiagonal elements can be taken directly from the elementary matrices. In this case, the 2 from the first matrix, the 3 from the second matrix, and the -1 from the third matrix. This rather nice property is not specific to this example, but is a result of the ordering of the matrices from row reduction. We'll call the new unit lower triangular matrix L. We now have that the matrix A equals the product of a unit lower triangular matrix and an upper triangular matrix. The upper triangular matrix U is simply a row echelon matrix, and the elements of the lower triangular matrix L are minus the multiples we use to zero out the elements to get the matrix U. We call this LU decomposition. Let's compute the LU decomposition for this matrix. We multiply the matrix by the identity matrix. We'll use this matrix to record our operations, and it will be made into the L matrix at the same time as original matrix is made into the U matrix. To zero out the element below the first pivot, we subtract 3 times the first row from the second row. We put a 3 in the corresponding position in the left matrix. To zero out the last element in the first column, we add the first row to the third row. We put a -1 in the corresponding position in the left matrix. Now, we subtract 3 halves times the second row from the third row. We put a 3 halves in the left matrix. We zero out the last element in the second column by adding 2 times the second row to the last row. We put a -2 in the left matrix. Finally, We add the third row to the fourth row, and we put a -1 in the left matrix. We now have the LU decomposition. It is not always possible or desirable to reduce every square matrix to row echelon form without permuting rows. For example, an element in the pivot position may be a 0. By multiplying the matrix A by a permutation matrix P, we can arrange the rows to ensure that there isn't a 0 in the pivot elements. In general, a matrix A has the decomposition P A equals LU. As we will see in later lessons, the inverse of the permutation matrix equals its transpose, and we have equivalent decomposition A equals P transpose LU. Now that we understand the mechanics of LU decomposition, we will end this lesson by seeing what we can do with it. By LU decomposition, the linear system AX equals B is equivalent to the system LUX equals B. We can solve this system in 2 steps. First, we solve Ly equals B for some unknown y. Then we solve Ux equals y for x.